Good morning, dear students. Today we shall see the element stiffness and load matrices. Element stiffness matrix results from element strain energy. The element stiffness matrix results from element strain energy. So when you take an elastic solid, it undergoes deformation under the action of body force and surface forces. When you take an elastic solid, it undergoes deformation under the action of body force and surface forces, right? Therefore, when it undergoes deformation, energy is stored in the solid in the form of strain energy. The expression for strain energy we had in the previous class. We derived the expression for strain energy. The expression for the strain energy of the elastic solid US equals to 1 by 2 into integral over the length of the solid into sigma transpose into epsilon dV. This is the expression. This is the expression we had for the strain energy of the elastic solid. Okay. Now, the same expression you can also use to determine the strain energy of the element when the solid is discretized into several finite elements. Right? Observe this figure, we have 3 finite elements. So therefore, you can determine the strain energy of each element. The strain energy of each element. Then sum up all the strain energies, you get the strain energy of the entire elastic solid. Okay. Now, the element stiffness matrix results from element strain energy. Right? Element strain energy. We had in the previous class the expression for the element strain energy. Okay. The strain energy of the element UE equals to 1 by 2 into integral over the length of the element sigma transpose into epsilon into dV. This is the expression. Right? Where dV is the differential volume of the element. So this term results in element stiffness matrix that we see today. So consider the element strain energy term. UE equals to 1 by 2 integral over the length of the element here. Integral over length of the element. Make correction. Integral over the length of the element LE into sigma transpose epsilon into A dx. What is A dx? It is the differential volume of the element. If you consider an elastic solid, with uniform cross section carrying a force say F, okay, the volume of the infinitesimal element of thickness dx located distant x units from the fixed support. You can determine what is the formula. The differential volume of the element equals to, because the cross section area is same everywhere throughout the length of the solid, A into dx. Hence you can write like this. This form will appear like this. Strain energy of the element UE equals to 1 by 2 into integral over the length of the element LE. Length of the element LE into sigma transpose epsilon into A dx. Okay? Where x is the Cartesian coordinate. Remember. Right? If you consider an axis with coordinate x, if you consider a coordinate axis x with origin here, right? We use this coordinate to define any point on this domain. What is the domain here? Geometry of the solid. Therefore, it is the global coordinate. Therefore, it is the global coordinate. What the finite element method says? It says that, right, according to the finite element method, the domain is discretized into subdomains. Therefore, for each subdomain, you have to establish a local coordinate system. Here I use the natural coordinate J. When you consider the natural coordinate J, what happens now? The length of the element is covered as J varies from -1 to +1. Okay? We know that sigma equals to EBQ and epsilon equals to BQ. Right? So when you replace sigma by EBQ and epsilon by BQ in this expression, it appears like this. It appears like this. Understand carefully. So sigma transpose equals to, how you get? Here I want to replace this sigma transpose. How you get? Sigma transpose equals to E is Young's modulus into BQ whole transpose. We know that AB whole transpose equals to B transpose into A transpose. This is the formula. According to this, I write sigma transpose equals to E into Q transpose into B transpose. Therefore, right, UE equals 1 by 2 integral over the length of the element into, in place of sigma transpose, Q transpose, B transpose into E. Next, into, in place of epsilon, what you write? Epsilon equals to BQ. Therefore, I write here BQ. Epsilon equals to BQ. And ADX I write as it is ADX. Understand this? Okay. Now, the element strain energy UE equals to 1 by 2 here. What Q transpose represents? Remember, Q is the element displacement vector. It is a column matrix. It is a column matrix. In general, we denote the element displacement vector Q as the transpose of row matrix having the elements Q1 and Q2. In general. Transpose of row matrix, therefore it is a column matrix. We defined element stiffness matrix as a column matrix. Understand? Now, here Q1 and Q2 represents the nodal displacements of the element. Q1 and Q2 represent the displacements of the nodes 1 and 2 in the element. Therefore, these Q1 and Q2 represent numbers. Right? They represent numbers with the displacement unit. Therefore, Q transpose, it is constant, it can come out. It can come out. Right? Now, it can come out. Integral over the length of the element B transpose into epsilon, B transpose into E, again, into B, into A, into dx, into Q. Remember here, A is also constant because the one-dimensional element, the one-dimensional bar element has uniform cross-section area. A is also constant. Right? Now what I do is, I compare this expression with the form, say UE equal to 1 by 2 into Q transpose into sub-bracketed term into Q. What is that bracketed term? Observe carefully. That bracketed term is viewed here. Integral over the length of the element B transpose E B A dx. This is the bracketed term. This I take and evaluate and see what we get. And see what we get. Understand? And see what we get. That we do. Okay. Let us see what happens. Now, what is the element strain energy? UE equals to 1 by 2 integral over the length of the element sigma transpose epsilon A dx. So therefore, how you write this equals to 1 by 2 integral over the length of the element. What is sigma? Sigma equals to E into epsilon, and epsilon is BQ. So therefore, I write sigma transpose E Q transpose B transpose B into Q into A dx. Now, what I told you, this equals to 1 by 2 into Q transpose into integral over length of the element. Observe carefully. Now, E B transpose B A dx into Q. This is the bracketed term. 1 by 2 Q transpose integral over length of the element E B transpose B A dx into Q. This is the bracketed term. Now I see what this bracketed term results. Okay. Now, this bracketed term, I say small k, then we see what this small k denotes. Small k equals to integral over the length of the element E A B transpose B dx. Okay. Now, I convert this global coordinate x into natural coordinate j. We know that j equals to 2 into x minus x1 by length of the element minus 1. Hence dj by dx, which equals to 2 by length of the element. Now what you write? This equals to the product EA is constant. It comes out integral over the length of the element. The length of the element. Okay. Now B transpose. Okay. What is B? We know that B equals to 1 by length of the element into a row matrix having the elements minus 1 and 1. Therefore, because it is row matrix, when you transpose it, it becomes a column matrix. Now I get 1 by length of the element into, now make it column matrix having the elements minus 1 and plus 1. Into, now what is B again? 1 by length of the element into a row matrix having the elements minus 1 and plus 1. Okay now, into, what is dx here? Dx equals to LE by 2 into dj. Understand carefully. Okay now this equals to EA now, right? So LE get cancelled with each other. Now what you get? EA by 2LE integral of EA by 2LE into integral of, now a column matrix with elements minus 1 and plus 1 into a row matrix with elements minus 1 and plus 1 into dj, as j varies from minus 1 to plus 1. Okay. Now this equals to This is the matrix of size 2 by 1 and this is the matrix of size 1 by 2. Therefore, we get a matrix of size 2 by 2. Now, EA by 2LE, multiply these two. Integral of, when you multiply these two, you get a 2 by 2 matrix. What you get? Minus 1 into minus 1 plus 1. Here minus 1, here minus 1 plus 1 dj. As I varies from minus 1 to plus 1. So why you take the limits minus 1 and plus 1? Because when you take a one-dimensional element connecting two nodes, the length of the element is covered as I varies from minus 1 to plus 1. Therefore, I take. Okay. Now, this matrix comes out integral of dj. It is simply j. Impose the limits minus 1 and plus 1. You get 2. Therefore, EA by 2LE into this matrix into 2. So, 2 get cancelled with each other. And ultimately, what you get? You get simply EA by the length of the element into a matrix having the elements 1, minus 1, minus 1, plus 1. What is this matrix? I say small k. EA by LE, what it represents? It represents stiffness. It represents stiffness. EA by LE, what it represents? Stiffness. Right? Hence we say K, element stiffness matrix. Element stiffness matrix. E is Young's modulus. We express in so many Newton per meter square. Then cross sectional area of the element we have to take in meter square. Length of the element we have to take in meters. When you express E in Newton per millimeter square, cross sectional area you have to take millimeter square and length of the element in millimeters. Understand? Now the element stiffness matrix K equals to, you have to remember, EA by L into a 2 by 2 matrix having the elements 1, minus 1, minus 1 and plus 1. Very, very important. If there are 10 elements in the domain, for each element you have to prepare the element stiffness matrix. If there are 10 elements in the domain, you have to prepare for each element stiffness matrix. Okay, now this is the element stiffness matrix. Okay, na? This is the element stiffness matrix. Right? Now, element body force vector. Element body force vector. We know that the work done by the body force is integral over the length of the solid U transpose F A dx. Observe carefully here. What U represents? U represents what? U represents the displacement at any point in the one-dimensional element. If you take a one-dimensional element like this, connecting two nodes, say 1 and 2, U represents the displacement at any point on the element. It is the unknown displacement. Okay, unknown displacement. U is the unknown displacement at the point of interest. Okay, integral over the length of the solid. the length of the solid, U transpose FA dx. What is F here? It is the body force per unit length. I told you, when you take a one-dimensional solid like this, okay, its weight is the body force. The body is under gravity, therefore its weight we have to consider. When the weight is considerable, you have to take weight into consideration. Right? If it is a weightless solid, if it is a weightless solid, if it is not heavier in weight, then we neglect weight of the solid. Okay, now, right? Now, the body force F, how we define? The body force F we define as the force per unit volume. F is the body force per unit volume. It is not per unit length. Force per unit volume. It is not the force per unit length. It is the force per unit volume. Okay. In this case, if you see, A is the cross section and L is the length of the solid. Then what is the volume of the solid? Simply AL. If F is the body force per unit volume, what is the total body force of the solid? Simply FAL. FAL is the body force of the solid. Okay, na? Right. Now, the work done by the body force is, what is the expression? Integral over the length of the solid U transpose into FA dx. So why we take minus here? Because the work potential is negative. Right? Okay. We know that U equals to N1 Q1 plus N2 Q2. N1 Q1 plus N2 Q2. Okay. Now, what are N1 and N2? They are the shape functions. What are Q1 and Q2? They are the nodal displacements. We write U equals to simply N into Q. N is the shape function matrix of size 1 by 2. And Q is the element displacement vector of size 2 by 1. Okay. To determine the work potential, we have to multiply the body force with the displacement. Okay. Now, here the axis X is taken vertically downwards because the self weight is acting vertically downwards. This is the origin. This is the origin. Right? Now, again take same expression. Integral over the length of the solid. Length of the solid. U transpose. How you write here? U transpose is same as U. Therefore, you can write N1 Q1 plus N2 Q2. In place of U transpose, you can write N1 Q1 plus N2 Q2. Okay. Into area of the solid is, cross-section area of the solid is constant. It is same throughout the length of the solid. Okay. And F is the body force per unit volume. It is also constant. So when you discretize this solid into several subdomains, okay, for each element, you have to determine the work potential due to body force. Hence, I take the expression for an element. So for an element, I write here integral over the length of the element U transpose FA dx, which equals to, because the cross section area of the element is constant, it comes out. Because the body force per unit volume is constant, it comes out. The product AE F comes out. AE is the cross section area of the element. Integral over the length of the element into U transpose is same as U here. Okay, because it is N1 Q1 plus N2 Q2. I write hence N1 Q1 plus N2 Q2 into dx. Okay, right. Now here U transpose, observe carefully here, U transpose equals Q transpose into N transpose, because U is expressed here as the product of two matrices N and Q. Whereas in the above expression, U is simply N1 Q1 plus N2 Q2. Hence, in place of U transpose, I write N1 Q1 plus N2 Q2. But in place of again same U transpose, I cannot write NQ. I can write Q transpose into N transpose, because here U is expressed as the product of two matrices N and Q. N is the shape function matrix and Q is the element displacement vector. What is the shape function matrix? And here N is a row matrix having the elements N1 and N2, and Q is a column matrix having the elements Q1 and Q2. Okay, right. So therefore, what you do here, in place of U transpose, I write U transpose, I write Q transpose into N transpose. Okay. Q transpose, it comes out here. Q transpose, it comes out. Now N transpose, it becomes a column matrix. AE into F, it is constant. AE into F into integral over the length of the element over the length of the element N1 into dx. Next, AE into F into integral over the length of the element N2 into dx. Right? Now, we have to convert this coordinate x into natural coordinate z. Okay. Again, we know that z equals to 2 into x minus x1 by length of the element minus 1. Therefore, dz by dx, what you get? 2 by L. Hence, you can replace dx. How? Le by 2 into dz. That is what I have written here. Dx equals to Le by 2 into dz. Okay. Now, in place of dx, I write Le by 2 into dz. Right? Now, you have to integrate N1 with respect to x. Integral over the length of the element. Integral over the length of the element. N1 into dx. So what you get? Say here because dx equals to Le by 2 into dz. Right? When I substitute, L by 2 comes out. Okay. Now integral of what is N1? N1 equals to, we know that 1 minus j by 2. Therefore, 1 minus j by 2 is written here into dj. What are the limits of j? Minus 1 and plus 1. If you evaluate this integral, you get Le by 2. Le by 2. And similarly, what is N2? N2 equals to 1 plus j by 2. If you integrate N2 with respect to x over the length of the element, what you get again? Le by 2 into integral of 1 plus j by 2. 1 plus j by 2. Remember, it is 1 plus j by 2 into dj. Okay. What are the limits of j? Minus 1 and plus 1. Then you get Le by 2. Now, from these two expressions, we can understand that integral over the length of the element N1 dx, integral over the length of the element N2 dx. You get simply half the length of the element. Therefore, in general, how you write? you can write integral of say Ni into dx. You get the length of the element by 2 as the length of the element by 2. Okay. Now, if you plot both shape functions n1 and n2 with respect to the length of the element, n1 is unity at node 1 and n1 is 0 at node 2. And if you plot carefully, because the shape functions n1 and n2 represent the linear functions, you get a variation like this, linear variation like this, you get straight line. How the diagram appears therefore as a right angle triangle. Determine the area of this right angle triangle, you get simply 1 by 2 into LE into 1 and LE by 2. Okay. Now, what you understand? You can understand that integral of n1 dx equals to LE by 2. Okay? That indicates the area of the triangle. Similarly, when you take n2 and plot against the length of the element, integral of n2 dx, you get LE by 2, which also indicates the area of the right angle triangle. Okay. So what we have learned in this particular class, we have learned about the element stiffness matrix. The element stiffness matrix results from element strain energy term. What is element stiffness matrix? EA by L into a 2 by 2 matrix having the elements 1, minus 1, minus 1 and plus 1. Okay. And we also derived element body force vector. Element body force vector. Right? This element body force vector, results from the work potential due to body force. Thank you. Thank you very much.